Day 64 notes, Algebra 2. I'd like to review from over the weekend how to combine like terms and then also how to predict what the graph of each polynomial is going to look like. So please, if you would, have a sheet of paper out to add these examples to your notebook and complete each of the problems as I work through them on the screen here. Feel free to pause and replay portions of this video if you need to. Okay, in problem number 1, we have several terms of a polynomial, and we know that we can combine like terms. So what I'm going to look for first is the term with the largest degree, or I'm sorry, the largest exponent, because this is going to represent the degree of the polynomial, and I know that its result should be listed first. So here I see an exponent of 3 and nothing larger than that. So I know that 8n cubed and a negative 10n cubed should combine together. When adding 8 and negative 10, we end up with negative 2, and we keep the n cubed as the exponent to this term. Notice that when we combine like terms, the exponent does not change. Okay, so that takes care of those two. The next largest exponent that I see is just an exponent of 1. I see negative 11n and positive 11n. And I also recognize that when negative 11n is added to a positive 11n, the result is 0. They will cancel each other out. So I don't need to write anything in my term. I'm sorry, in my polynomial next. Those terms cancel out. And finally, I have a positive 8 and a negative 1, which are like terms, and those two combine to make a positive 7. Now, as a quick additional review, this is what we would call a cubic binomial. Cubic because of the degree being 3, and binomial because there are 2 terms. Now, to make a guess or predict what the graph might look like, remember all that we need to concern ourselves with is this leading term, the term with the largest exponent, or the term that contains the degree of the problem. And so if we were to predict the shape, we should remember our rules from last week. And if you need to go back and look at the notes, you can do so. We most recently discussed them on day 62. This is the chart that we wrote for polynomial end behavior on day 62. Now in our problem today, or this first example, we have a negative leading coefficient because it starts with a negative 2 as our leading coefficient, and we have an odd degree. So when we have an odd degree along with a negative leading coefficient, these are the directions of the tails that the graph would produce. So I know that if I were to predict what the graph looks like, I'm going to draw one tail that points down and to the right, another tail that points up and to the left. And since this is a cubic function, it has a degree of 3. That means I can have as many as 2 turns to the graph. Now, I don't know exactly where those turns are going to occur, so I'm going to just put this dotted line here like this. We've got one big turn here, another big turn there, at most 2 turns. This is always one less than the degree itself. This would be a pretty good sketch. How about on your own, you try number 2 here. Combine the like terms and predict what the graph would look like. I'm going to pause the recording and resume it in a few seconds, and you can also do the same. Pause the video and resume playback shortly so that you can check your work. And here's a result that should be pretty similar to what you see. The totals come out to be 21p to the 4th power plus 18p cubed plus 4p squared. And for those of you that were checking, this is a quartic trinomial. Quartic because of the degree 4, and a trinomial because we have the 3 terms. So we can call that a quartic trinomial. Since it's a positive leading coefficient, since this has a positive leading coefficient and an even degree, the tails had to be pointing up. And since the degree was 4, we could have as many as 3 turns. 1, 2, and 3. Moving on. Try to answer these two questions before combining like terms in this particular example. Question number one, or part A, what type of polynomial is the sum or difference of two quartic polynomials? In this case, we have two quartic trinomials. These are both quartic trinomials, and we're subtracting them, so we're looking for the difference in this case. But this result would also be very similar to a sum. The sum mathematics is essentially the same as the difference. Instead of subtracting, we would be adding. So if we started with a quartic polynomial and subtracted another quartic polynomial, what type of polynomial are we going to end with? So think about that for a moment. If I start with r to the fourth power and I subtract something else with r to the fourth power, what's the degree going to be in the result of that subtraction? Well, hopefully you recognize that it's most likely going to be another quartic polynomial. I'm going to put a little star here though, because there's one way that we can actually add we could actually subtract and end up with something that's not a quartic polynomial. And if you can tell me about that tomorrow when I come back into class, maybe I'll give you some bonus points. If you can think of how we can subtract two quartic polynomials so that result doesn't become a quartic polynomial, think about that. Now for part B, I would like to describe its end behavior and sketch a graph. Well, in order to really complete that, I think it would be a good idea to complete the math. Now what I'll do is I'll copy the original problem, but I'm going to distribute this subtraction sign and drop the parentheses at the same time. So I'm going to rewrite this first group as r minus 3r cubed plus 10r to the fourth. And then when I distribute this negative sign, it goes to each of these terms. It's going to make our math just a little bit easier. So we have a minus 13 r to the fourth minus 12r cubed. Now we can combine like terms. And 10r to the fourth minus 13r to the fourth comes out to be negative 3r to the fourth power. That takes care of those two terms. Then we have a negative 3r cubed minus 12r cubed. That's minus 15r cubed. That takes care of both of those terms. Finally, we have an r with no other like terms. That's a positive r, and a negative 13 with no other like terms either. So this is the resulting polynomial, which again is another quartic polynomial, in this case with a negative leading coefficient. So if I were to predict what this graph would look like, I know that because of the negative leading coefficient and the even degree, that the tails have to be pointing down. And since it's a fourth degree polynomial, I could have as many as 3 turns. So this looks like a pretty good sketch of what that polynomial would look like. I'd like for you to try number 4 on your own. Without completing the math first, tell me what type of polynomial would be the sum or the difference of two cubic polynomials. Again, in this case, we're subtracting two cubic polynomials. So what likely is the sum or the difference of those two? And then in part B, go ahead and combine those two and sketch a graph. Again, pause the video right now and try this on your own, and you can resume playback in a few moments to check your work. Okay, and there we have it. The type of polynomial when we add or subtract two cubic polynomials is most likely going to be another cubic polynomial. Again, with a star here because there is, I can think of one case where the result from a difference, or when we subtract two cubic polynomials, we might not end up with one. So again, if you can think of that example, go ahead and tell me about that tomorrow in class. Now, in part B below, I went ahead and distributed the negative sign to each of these 3 terms. So that turned into a negative 12, negative 4b cubed, and then a positive 4b squared because of the distribution of the negative sign. With all 6 of those terms laid out, we now have a series of terms that can be added or subtracted together, and our end result is something that looks like this. With a negative leading coefficient and an odd degree, I knew the tails of the polynomial had to point like this, down and to the right and up and to the left, with as many as 2 turns to the graph. 2 turns because the degree was 3. And we're allowed to have 1 turn less than our degree. So please make sure that you understand what we've done in problems 1 through 4 today. Review the video, replay parts of it if I went too fast, and even talk to a neighbor to make sure that you understand each of the techniques. We need to move forward this week, and I want to make sure that you have a good, clear understanding of each of those 4 problems. Now we have just 4 more problems to complete to finish out this video, and I'd like for you to take a look at them next. This time, however, we're not going to add or subtract 2 polynomials together, but instead we are going to multiply 2 polynomials together. And before you even complete the multiplication, I'd like for you to predict what each graph would look like after multiplying the polynomials together. So looking at these 2 polynomials that need to be multiplied together, could you imagine what the graph of this equation would look like? Well, hopefully you recognized a few patterns from our products last week. Anytime that I have a leading coefficient, or I'm sorry, a leading term that's a 3p squared in this case, multiplied by another leading term, it's those 2 leading terms that multiply together to result in our leading term of the next polynomial. So this 3p squared times another 3p, that's going to give us our leading term of our next polynomial. And in this case, p squared times a p-value is going to result in something p to the third. Actually, it's going to be 9p to the third when I multiply those 2 together. So this is really the important term in the polynomial. This is what tells us what the graph might look like. And so without even doing the multiplication, I know that this sketch would look something like this. Positive leading coefficient with an odd degree, the tails point up and to the right, down and to the left, and we can have as many as 2 turns. Now, to verify this guess, we should go ahead and do the multiplication. So I'm going to erase this. I'll leave my guess in place, but I'll erase that work there. And I'll remind you at this point that in order to multiply polynomials that are bigger than binomials, we should use the table method. So along the top edge of the table, I might write 3p squared plus 7p plus 7. Oops, that's a minus 7p. Okay. And then down along the left edge, I'll write 3p and a positive, oops, sorry, I'm getting that wrong again, and a minus 8, a negative 8 for the subtraction of 8 here. This gives me little pockets or grids that I can work through now, and I can calculate the results for the product of each of these terms. Okay, and to check our work here, I'm going to leave this guess up on the page, but I would like to check to see what the product of this polynomial is. We can verify whether or not the resulting polynomial will produce a shape that looks like this. The thing to remember is that when I'm multiplying a polynomial times another polynomial, if they're bigger than binomials, then we can't use the foiling method, and we have to use the table method. So what I might do here is write 3p squared plus, oops, minus 7p plus 7. We'll put that along the top. And then along the left-hand side, we can write 3p and a negative 8. And this gives me a grid to work off of to complete all of the multiplications necessary in this polynomial multiplication. Now I'll complete the calculations here silently, and you should work along with me. And when we combine our like terms, in this case, the like terms showed up along these two diagonals here. With the like terms combined, we ended up with a polynomial that looks like this. And again, with a polynomial, all we need to focus on is its leading term to produce a sketch of the graph. And sure enough, the leading term is a positive leading coefficient with an odd degree, and a positive leading coefficient with an odd degree produces a graph that looks like this. The tails point up and to the right, down and to the left, and we can have at most 2 turns here because our degree is 3. So our predicted shape of the graph looks to be pretty good. Let's try another one. Can you predict what the shape of this graph would look like? Please make your guess now, and go ahead and multiply the two polynomials together to verify. I'll pause the video and you should do the same. You can resume playback in a moment to check your work. And hopefully your result looked something like this. The product of 3r squared and 3r produces an r to the third power, and we could have used that to guess what the shape of the polynomial would look like. We verified that by multiplying the two using the table method, and this is the result from the product of those two polynomials. It does indeed contain a leading coefficient of a positive number and a degree that's odd. So when our leading coefficient is positive and our degree is odd, we have the tails pointing up and to the right, down and to the left, and this would be a good sketch of that graph. Let's go ahead and try 2 more, and I'll have you do these on your own, and we can check them tomorrow in class. Here's the first example. Please write it down. And here's the next example. Please make sure that you write this one down as well. Thanks for your cooperation today, and make sure that you have this work completed so that we can talk about it tomorrow.